In the last lesson we learnt what K-maps were and how they were used. Today we're going to look how to solve our very first K-map from start to finish. By the end of this lesson you'll know exactly how to convert from truth tables into K-maps and simplify Boolean expressions. So today we'll look at reading truth tables, drawing a two variable K-map, grouping neighbouring ones and writing simplified Boolean expressions. If you can learn these 4 skills, these are the foundation of every K-map. So including the larger maps we'll look at in the later series. So we start off with the truth table. The truth table tells us the output of every possible combination of our inputs. I would assume you've seen this before if you are studying IB Computer Science. Our job is to transfer these outputs into a K-map. We start off by drawing our grid. A 2 variable K-map is simply a 2x2 grid. The rows represent A and the columns represent B. Each square corresponds to 1 row in the truth table. Then we copy our outputs from the truth table into the correct positions. Notice that we're only transferring the outputs, not the inputs. So as you can see, we've now got 0, 1, 1, 1, which relates exactly to our outputs of our truth table here. Next is the most important part. We need to group together our neighbouring ones. Okay? We look for groups of neighbouring ones. The groups must always contain a power of 2. That means either 1, 2, 4, 8 or so on. So you can't group 5 of them together or 6. It has to be a power of 2. In this example we can make 2 groups of 2. Each group represents a simplified part of our Boolean expression. Together they can give us our final answer. Instead of writing these 2 separate terms, we can reduce the expression to simply just A plus B. So this is what we would have started off with, and this is the same. So we have simplified our table from A not B and A or B and A or B not B, sorry. Okay? The reason it is this is because we've got 2 1s here and 2 1s here. So we've got A, because it's always 1 when it's on A, and B, because it's always 1 when it's on B. So that is our expression, and that's how we found it from grouping together these ones. Okay, and that also is a much simpler circuit than if we had all of this and we've got this. It would produce the same output, but as we learned in the last video, it costs more, it would have delays, and I can't remember the third thing, but it would be better just to have 1 gate rather than, I can't remember, count there, 1, 2, 3, 4, 5, 6 gates. Cheaper, quicker. So, golden rules. Groups must contain powers of 2. Make groups as large as possible. Everyone must belong to a group and never group diagonally. So here is a practice question. So pause the video now. Draw the K-map yourself before watching the solution. So this is our K-map. We've grouped together our 1s and we've got 1 here, 1 here. Both 1s are located where B equals 0. So B remains constant while A changes. This allows us to simplify our expression to simply not B. So the answer is true when it is not B, so 0. So today we've transferred a truth table into a K-map. We've grouped our neighbouring ones and we've simplified our Boolean expressions. So well done, you've now completed your first K-map from beginning to end. In the next lesson we'll look at K-maps and using grey code ordering and why that matters when we move on to our larger maps. If you haven't subscribed, please do so already, and you'll find in the description a free revision sheet and practice exam questions linked in the description. Thank you.